Okay, so here's the E&M free response problem from the 1988 test. And so here we've got an isolated conducting solid sphere of radius A, shown above, is charged to a potential of V. Determine the charge on the sphere. Okay, that's part A. So let's just do this a part at a time. Let me find where I am on the screen here. So for part A, you're given this conducting sphere, and it's got a radius of A. So I'll just show it as a sphere here. And it has a voltage of V. And we want to know, what is the charge on it? Well, voltage is equal, and this you just have to have memorized, or it could be on your equation list, is equal to KQ over R. Right? That's the basic equation. This acts like a point charge. And so you just solve for Q. Q is equal to V times R, but what is R in this case? It's A. And you divide, and what's the matter? Oh, you guys, I'm recording this. It's so disappointing. All right, divided by K. And that's how I would do it. So there you go. Now, hey, on the AP test, you quite often they don't want you to spend a lot of time working with a calculator. So a lot of the problems are like this, where you derive expressions rather than actually come up with a numerical answer. But when you think about it, what would you do next if this was a problem with numbers in it? Then you would whip out the calculator and plug in all the numbers, and you would get an answer, and you would take a lot of time to do that. So, you know, this is actually much nicer. All right, so that's your answer for part A. Then it says this. Two conducting hemispherical shells of radius B, so here's our, are then brought up and without contacting the solid sphere are connected to form a spherical shell surrounding and concentric with the solid sphere as shown below. The outer shell is then grounded. Now what that means if it's grounded, well, let's just take a look at what happens here. So here's my charged sphere with this much charge on it. And then what I do is I put this shell around it. So here's the shell. And we're going to give it, this has a radius of A, and this has a radius of B. Now, this has so much charge on it. Let's pretend like it's positive charge, because it didn't really say. But we can say it's positive charge. And so what would happen is this. If it wasn't grounded, what would happen is that you would get an electric field in here. Okay? And so what would happen is on the inside surface of this conducting shell, you would get negative charge on the inside. And the electric field would terminate there. On the interior of the shell, you would have no electric field in here because it's a conducting material. But this negative charge came at the expense of putting positive charge on the outside here. Okay? Now normally this electric field would just continue on, but they grounded it. They grounded it. Now what this means is that all of this charge on the outside is now, remember they want to get away, and it's a conducting material, so they're free to flow. And so they just go whoop into the ground. Whoop. They actually make noise as they travel through the conductor. And so what happens is that because it's grounded, these positive charges go away. Now what it means when you ground something, that means that you have 0 volts now. So the voltage here is 0. Now here's one way to think about why it's 0. There's no more the E field out here is equal to 0. The E field out here is 0. So from infinity to this surface, you don't do any work against the electric field because there's nothing. So its voltage is 0. So this is a situation you have. Now for part B, it says, by means of Gauss's law, determine the electric field in the space between the solid sphere and the shell at a distance r from the center. Well, that means you're in here. So here's my Gaussian surface in here. Now all this stuff I talked about it being grounded and all that, it doesn't matter. None of that mattered because all you care about is the charge inside. So when you use Gauss's law to figure out what the electric field is in here, you say E dot dA is equal to the charge enclosed over epsilon naught. And now you just say, okay, well, this is just E times, well, the area of a sphere is 4 pi r squared. And that's going to be equal to the charge enclosed. Well, how much charge is enclosed? All of it. And so I could use this charge up here, which is V times A over K. And this is going to be over epsilon naught. Now, I could probably clear that up a little bit. And so E is equal to VA over K. And what is epsilon naught? It's 1 over 4 pi K. Hey. And so this is 1 over 4 pi epsilon naught. Now what did I leave out? This is the charge over epsilon naught. Oh, and then what I'm going to do is divide by 4 pi r squared. So 4 pi r squared. And that's my expression for the electric field. Of course, E, here the 4 pi's cancel. And the k's cancel. And I get V A over r squared. Is that the answer? So that's your expression. Now when I'm looking at the solution guide here, the solution guide is pretty forgiving because they let you do it KQ over r squared. They give you full credit for that because why? Because if you made a mistake in part A, they don't want it to carry on into part B. So if you did part B right, even if you did part A wrong, you can still get all 4 points. Did you notice that? So when you're grading your practice test, make sure that you read this carefully and don't, you want to be fair to yourself. They are extremely fair on this. Okay, now part C. I'm almost done. Okay, part C, determine the potential of the solid sphere relative to the ground. So we're going to start at the ground and we're going to go inwards like this. So remember that delta V is equal to negative E dot ds. Now that's the basic equation. And now we're going to apply that. So delta V is equal to negative, well, you got VA over r squared. So VA comes out, the integral of r squared. Now ds is just going to be dr, turns into dr. And we're going to go from B to A. We're going to go from here to here. We're going to figure out how much potential we've got starting here and going in there.
Wait, is there 1 over r squared?
Oh, this should be a negative 2. Yeah, 1 over r squared, which is r to the negative 2. Thank you. Okay, so now delta V is equal to negative VA. And then what do you got? You got negative 1 over r, measured from B to A. So these negatives cancel, and you get VA over A minus VA over B. And you can, in the solution guide they express it a little bit differently, and they have various different ways of doing it. So there's more than one way to do this. Now I got 2 minutes left, so I'm going to do part D now. So, what's the big idea? What do you have to remember? Voltage. How do you calculate voltage if you know the electric field? Now, if you had attempted to use this, you would have gotten a lot of partial credit. Even if you screwed up this, you're going to survive with partial credit on the AP test and in college. You've got to show what you know. So don't abandon it. Give it a shot. Okay, here's part D. Am I still on camera okay? All right. It says, determine the capacitance of the system in terms of the quantities given. Okay, well, capacitance is equal to Q over delta V. Okay, and so Q, in terms of the quantities given. Now, write this down. Did you write this down? I hope you did, because if you didn't, you're being a bad test taker, because you get partial credit just for knowing the definition of capacitance. Now Q, so now Q is equal to VA over K, and delta V is equal to this, I don't know, I'll go V minus V sub A over B. I don't know. Now you can clean that up if you want, but you did what they asked you to do. You express the capacitance in terms of the quantities and constants of nature. Okay, so that last, let me zoom all the way out. So in this problem, look how much ground they cover. They cover the voltage around essentially a point charge. They cover Gauss's law. They covered the definition of voltage. And they had capacitance, all in one problem. So, that's the AP test for you, folks.